Okay, we're back at it. I had a loose end to tie up about surface area. I'm sure you were resting fitfully last night because of it. So let me ease your pain and explain it in its entirety. What I left out yesterday was what happens when we take a function and revolve it around the y-axis. We did one with the x-axis, so this time we're going around the y-axis. So a little sketch never hurts. So we're going to do this y equals x squared from 0, that's the smiler, from 0 to square root of 2 on the x value. And we're going to take that around here. So we are going to get this right here when I go around the y-axis. So I'm interested in that figure and I want its surface area. So it's like a bowl. So I'm handing you the bowl and you're sliding your hands all around the sides of the bowl and are wondering what the surface area of it is. And you'll recall how we did that. Here was the function that we revolved. And we take a ribbon and we put it around our bowl just like we did yesterday with our, what was that? That cup. Well, anyway, so, and if I take that ribbon off and lay it across, we recognize that the length of the ribbon was the same as the circumference, 2 pi r, and the width was the tricky part yesterday, no surprise today, but that was the arc length from here to here. So the length of the segment, which was 1 plus the derivative squared dx. Now, when we go around y, when we were using discs and washers, this changed to dy, but I just want to emphasize when we're doing surface area, it does not switch to y and dy, because you'll notice, let me enlarge this surface area here, I mean the segment here, and if I wrap the ribbon around, so I'm just drawing the same thing a little bigger. Right here, the thickness of that ribbon is the same as it was when I took the ribbon the other way and went this way. Do you see that it didn't matter whether I went in the x direction or wrapped around the x-axis or the y, I'm still using the thickness between these two spots, which is also a dx. And it also will require me to use, we're going to add up these segments all across this, and we're going to let these segments shrink away to infinitesimally small values as we do with the integral. But notice these little segments are still, even though we wrapped it around the y-axis, they're still going to add up from 0 to square root of 2 on the x-axis. So it acts a little differently than you might think, having seen how it acts with disks. So in a way it's simpler because the surface area is always going to involve dx. So that's nice. One less thing to worry about. So we're going to have a 2 pi r, the radius, and then this. It looks like it'd be a horrible thing to integrate, but we pick ones that are integratable, so we won't torture you too much. So what is the derivative of this function? Well, it was x squared, so the derivative is 2x, and when we square that, we get 4x squared. So that'll become a 4x squared when I rewrite this. And the r is, let's going back to this picture, the radius of this is right there, so it goes from here to here and it hits the point xy on the function, so that you'll see is the value, and it's red, and the x-axis, so it's just an x. So not too hard in that respect. So we have x 1 plus 4x squared under the radical dx. And so once again, let me emphasize, when you wrap these functions around the y-axis, you still take the derivative with respect to x, and the whole integral is with respect to dx. So no matter which way you wrap. All right, so let's go ahead and calculate this. I'll get you to a point where we went. U equals 1 plus 4x squared. Du equals 8x dx. So coming up here, I need an 8 in my problem. So I stick in 8 in here, and a 1/8 out here. So 2 pi over 8 becomes pi over 4. And this integral becomes square root of u du. And from there, we'll integrate. Square root of u is u to the 1/2. It integrates u to the 3/2 times 2/3, etc., etc. And we didn't even finish it because it becomes like monkey math doing integrals, plugging in numbers. So it comes out to 13 pi over 3 if you want to test your skills. I was more interested in the setup. All right, so let's see how we finished our class. Oh yeah, I assigned 2 problems from that concept. Let's see if I wrote them down for you. I hope these are right. I'm kind of doing them from memory. So these will be your problems. So I think they're the same as everyone else's. I want you to find the surface area. One of them we're going around the x-axis, and one of them we're going around the y. So you can see which is which here. Find the surface area. Taking this function between 4 and 9 and revolving around the x-axis and finding the surface area of the figure that ensues. And here is the surface area of 9 minus x squared when you revolve that between 0 and 3 around the y-axis. We observe what the surface area is from that. So set these up like I have trained you and bring those with you on Friday. All right, the rest of the class we spent on a new topic called work, and we just sort of I explained one problem, and the students did one problem, and we're not really ready to do a homework section on that yet. So here's what we did together. So if you would take notes on this, that'd be helpful. It turns out that the work we learned in physics class was the product of 2 things. Do you remember what they were? Of course you do. Force and distance. Work equals force times distance. Everyone knows that. And in physics class, we would say, well, say a spring, we apply, I don't know, a 3 Newton force to a spring, and or let's just say we apply a 3 Newton force to a box, and the box is going to move 3 meters. So what was the work involved? We'd go 3 newtons times 3 meters is 9 Newton meters, and that was we renamed joules. So that's what happens when the force is constant. But in real life, the force is not usually constant. For example, say I had a spring and I'm going to pull it. And it starts here, and I'm going to pull it to here. And as I'm pulling it, at first it goes real easily. But once I get here, down to here, it's really hard to pull. I start to shake and cry and everything, and because it's so hard. And so what I'm trying to say is the force is variable. It's not a constant force. When you pull a spring, first your pull is not very forceful, and then it becomes harder and harder, and you apply more and more force to pull the spring. So it varies, the force varies. So what we do is we calculate the force, say, to move the spring from here to here, very small amount. And then we calculate the force from here to here, and then from here to here, and we have how many divisions? Let's say, an infinite number. So that leads us to our integral. So our integral is what sums up an infinite number of things. So we're going to go from where the spring starts to where the spring ends. And we're going to do the work, and it's going to be force times distance. And the distance is going to become our dx, because it's going to be very small increments of distance. So we're all set to do a spring problem if we recall what the force for a spring is. And Mr. Newton told us that with a spring, the force of a spring is only going to work for springs, is going to be kx, where k is a spring constant, which is given, or you can calculate it, and x is the distance that the spring is pulled. So keep that in mind. That's Hooke's law. And you've actually had that in physics class. All right, so let's do two spring problems, and if you would get them down and understand them, that'll be all that's required. We have a 200 Newton force that stretches a spring 25 centimeters. Oops, there, 25 centimeters. All right, find the work to stretch the spring from 15 centimeters to 40 centimeters. All right, so once you write that down, I'll start it on another sheet of paper. All right, pause it if you need it. And it turns out that whenever you have a work problem, you can begin by saying work equals force times distance, or in calculus class, work equals the integral of force dx. So that will get you started no matter what kind of force problem we're doing. So in this one, our force happens to be kx, spring constant times the distance moved. And we'll be doing other types of forces, like the force of gravity and the force of mostly just gravity. We'll be using other forces in other problems, but for today, we're just doing the force of a spring. So in this problem, you notice that it told you in the beginning that the 200 Newton force stretches a spring 25 centimeters. Well, what's that for? That is enabling us to find our K. So we're going to work over here on K, because we know force equals Kx according to Newton, and it said a 200 Newton force will stretch the spring 25 centimeters. Notice I wrote it in terms of meters, because Newton's has to work in meters. So when I divide by 0.25, I get 25.25 into 20 goes what? So I think that's, is it 800? Do we get a K of 800? 200? Yes, that's right. So now that we've got that, we come back and we plug that in our work here. So we have that formula to work with. And we're going to use the limits of integration. It had to go from 15 centimeters, which I do in terms of meters, to 40 centimeters, which is in terms of meters, 0.15 and 0.40. So when I integrate that, I get 800x squared over 2. And I plug in these numbers. And when I do all that properly, I get 55. And work is measured in joules when we're in the metric system. All right, I have one more example. I'll have to do it on another video. See you in a sec.